12s. Welcome to Thursday. My apologies that I can't be there today, but I am in a little math PD. So what we're going to do today in this video is we are going to finish the lesson from yesterday, which was, I'll scroll to the top here for you, which was lesson 3, sketching graphs and functions. Yesterday we went through about the first half of this lesson. So today I am just going to go through the final 3 examples here today. Okay, so to begin with here, we're looking at example 3, which says state the parent function and transformation that was applied to y equals 2 root x minus 4, then graph the transformed function. So what I'm going to do here is I am going to use mapping notation to apply the transformations and come up with our transformed function here. So like looking at that graph there, or that function, our parent function here is going to be f at x equals, it's going to be a square root function. When we're using mapping notation, typically what we're going to do here is we are going to start with a nice little table of values. Okay, and in this table of values, we're going to pick some values that are good for our square root function. Those are going to be 0, 1, 4, and 9 because those values are perfect squares. Sometimes what I also like to do is I like to put the equals root x. That's how we're going to get our y values there, is I'm going to sub each x value into that equation there to determine our y values. The square root of 0 being 0, the square root of 1 being 1, square root of 4 being 2, and the square root of 9 being 3. Okay, so those are the coordinates of our parent function. Now what we're going to do is we're going to take a look at the transformations in our function here. Take a look at the transformations, determine what our mapping notation is going to be, and then apply mapping notation to our parent function coordinates. So to begin with, we'll just identify what the transformations are. The first transformation is this 2. That is a vertical stretch by a factor of 2. And then this minus 4 here, that's going to be a shift down 4 units. Okay. Now these are our C value and our A value. So applying this to mapping notation, I'm just going to do mapping notation down here because that's where I have some space. Our mapping notation is x over k plus d and ay plus c. Now the only values that we have here, the only ones that we have in our function are a and c. Okay, our a being the 2, our c being the negative 4. And so I'm going to write that out in my new table of values. So my table of values for my transformed function, which is y equals 2 root x minus 4. My transformed function, my x values are all going to remain the same because I have no k value or d value. And my y values are going to be, my a value is 2, so it's going to be 2y minus 4. That's that shift down of 4. Okay. Because my x values are not changing, I'm just going to rewrite all of those 0, 1, 4, and 9. And I'm going to apply the transformation to my y values. So those are going to change. So I'm going to multiply each y value by 2, then subtract 4. So that's going to be 0 times 2 is 0, minus 4 is negative 4. 2 times 1 is 2, minus 4 is negative 2. 2 times 2 is 4, minus 4 is 0. And 2 times 3 is 6, minus 4 is 2. I'm going to plot those points now, and we're going to see what our graph looks like. 1, 2, 3, 4. 1, negative 2, 0, 4. Or sorry, 4, 0. And 9, 2. And so if I'm sketching my curve of that root function, that transformed root function, that is what it is going to look like. Okay? Perfect. All right, so that's sketching a graph using mapping notation. Next here, we are going to look at the graph root x is compressed vertically. Okay, so what we're going to do here is we're going to determine, I'm just going to tell you here, and then I'll read the question. Typically, if I'm reading or answering a question, what I like to do is I'll figure out what the question's asking. So like this question's asking me to determine the equation that results from the transformations. Okay, so if now knowing that, now I'm going to read the question and figure out the equation that I'm going to use. So I know it's going to be y equals. Now I'm going to read each kind of transformation here. So it says compressed vertically by a factor of a half or 0.5. So I'm going to do 1 over 2. Okay, that's my compressed vertically by a half. Then it's reflected in the x-axis. That's a vertical reflection. So that half needs to be negative. Then it's shifted 1 unit to the left. Okay, now notice this is a square root function. So I'm going to go root. It's shifted 1 unit to the left. So that's going to be x. Whoa. Plus 1. Okay, that's going to be a shift to the left. Now that's the equation of that transformed function with those 3 transformations applied. Okay. And I think, let me just see here. Oh no. Yeah, we're good. Okay, so let's continue here. Last one here, last example is we're going to graph 1 cycle of sine of x and the transformed function. So we'll graph 1 cycle of f of x equals sine of x and the transformed function. So it wants us to graph both pieces here. I'm actually going to erase that part there, and I'm going to do this one in red and this one in green. Okay. So again, it wants us to graph the parent function, which is f of x equals sine of x. Okay, what does that parent function look like? So again, we're like building off of what we would have done in your functions course. So most of you would have seen these functions before, okay? You would have seen the sine function before. And so thinking back to when we did the sine function, when you want to graph a sine or a cosine function, you're looking for 5. You have 5 kind of key points here. And those key points, the x values of those key points, are at 0, 90, 180, 270, and 360. And if you think of what a sine function looks like, again, I talked about this at the start of yesterday, but you need to know what these functions look like. It starts at 0, goes up, goes down, and then comes back up. So at 0, my y value is also 0. Now, you need to know the characteristics of these functions. At 90, the maximum of my sine function is 1. My graph then comes back down to 0 at 180 degrees, goes to a minimum of -1 at 270 degrees, and returns back to 0 at 360 degrees. And that's roughly what my function looks like, okay? This graph is really unfortunate that it is so small, or that I don't have much negative. So what I'm going to do is I'm actually going to go, this is going to be a half, 0.5. This is going to be 1 unit. So roughly if I'm going down here, probably this is going to be -1 about here. Okay? Is that about right? Probably could be a little bit more. See if I can fix that just to make it, try to make it a little bit more accurate. If I go like this, just extend this line down a little bit. Let's go roughly here. And then say there. So we'll call this -1 here. Okay, so what that original function is going to look like is it's going to go up, down, all the way down, and back up. So roughly like this. Okay. All right, and so now what we want to do is we want to graph the transformed function. So we want to apply the transformations that are given here. So the 1 over 2, this first one, is going to be a vertical compression by a factor of 1 over 2. My second one here, this 2, is going to be a horizontal compression by a factor of 1 over 2. Okay, so now how do these apply in my mapping notation? Well, and I'm going to zoom in a little bit here. This is my A value. This is my K value. So in my mapping notation, which is X over K plus D and AY plus C, this becomes X over 2 and 1 over 2 times Y. Okay, which simplifies to, well, X over 2 stays the same and Y over 2. So this is the mapping notation that we're going to use. So to graph the transform function, we have Y equals 1 over 2 f of 2x. Okay, what this looks like is I have x over 2 and y over 2. Now, basically all I'm doing here is I'm dividing every x coordinate by half and every y coordinate by half. So 0 divided by 2 is 0. 90 divided by 2 is 45. 180 divided by 2 is 90. 270 divided by 2 is 135. 360 divided by 2 is 180. Continuing here, 0 divided by 2 is 0. 1/2, 0, negative 1/2, and 0. We can just plot those points now. And this is what my transformed function looks like, that little green one there. Now, if we know about sine functions, it's going to just continue in that pattern over and over and over again, forever and ever and ever. Okay? So that's a little bit on transformations and sketching functions. If you did miss the start of the lesson yesterday, you can take a look back on the OneNote or come in and ask me questions tomorrow at lunchtime. Okay? That was about 13 minutes. Okay, we're going to roll right along into our inverse functions lesson. Okay, cover this. Our unit test is going to be next Thursday. All right, so we have a couple lessons left to go. We'll have a review day next week, and then our test is going to be next Thursday. So just to kind of give you a heads up on that. Okay, I'm going to roll through this pretty quickly. The lesson is posted here on D2L, so if you do want to go back and take a look at any of these parts, you can rewatch them, or you can come in and see me at lunch tomorrow. I will also take questions at the start of class tomorrow about any of the homework from transformations and or inverse functions. Okay, so please feel free to ask me any questions that you have. Okay. Typically when I start this lesson, I like to start by looking up the definition of what inverse means. I don't have that capability right now with on my tablet to kind of pull that up. But basically, what inverse means, if you were to look it up on your phone or look it up in a dictionary. Actually, you know what? Pull it up on my phone here quick. Inverse definition. Inverse definition means, so inverse means it is opposite or contrary in position, direction, order, or effect. So basically means the opposite or reverse of something. Okay, so when we think of opposite in terms of math, okay, usually we could think of like inverse operations or opposite operations. So like the opposite of addition would be subtraction. The opposite of multiplication would be division. So those are inverses or inverse operations. Now the inverse of squaring something would be square rooting something. Okay, so we have inverse operations in math. Now when we talk about inverse in terms of functions, we're talking about kind of like the opposite points. So when we're looking at a function is usually or typically looking at like a coordinate, x, y. And you'll remember from last year, hopefully, or from your functions course, that to find the inverse, typically what we are doing is we are swapping x and y. So we're reversing them, or they're in opposite order. Okay, that's what inverse means. And so what we're going to do today is when we discuss functions, when we talk about functions, we have three ways of kind of looking at functions or three ways of representing functions. Our first way of representing a function is given a table of values. Our second way of representing a function is given a graph. And our third way of representing a function is given an equation. So we have these three ways of representing functions. And what we're going to do today is I'm going to show you how to determine the inverse of a function in each form, right? So here we go. Let's rock and roll. If we're given a table of values, how do we determine the inverse of that function? Well, we have our table of values here. Okay, I kind of mentioned it at the beginning there, right over here. Okay, right here. I'll highlight it again for you. We're going to swap our x and y's. It's as simple as that. This is my original function. My inverse function is just going to be those points, but swapped. -16, -2, -3, -1, 0, 0, nothing to change there. -1 and 1, 0 and 2, 9 and 3. Notice that all we did was we swapped those values. That's all it is for a table of values. You're just literally just swapping your x and y coordinates. Okay? Pretty straightforward. Let's bring it over to a graph. Okay? With a graph, we're going to do this actually really similar. Okay? In a really similar way. Now, there are two kind of specific ways that you can find the inverse of a graph. I find it easiest to just kind of pick a few points on the graph, write those coordinates out. Okay. Write those coordinates out and then swap the x and y in each of those coordinates to come up with new coordinates. So with the first one there, we have -4, 4. I'm going to swap those and I get 4, -4. Which is right here. That's 4, -4. I'm going to swap the 0, 4. I get 4, 0. This is this coordinate right here. And I'm going to swap the -2, 0, and I get 0, -2, which is this coordinate right here. So for an inverse function, given a graph, basically what you want to do is you just want to pick some coordinates, swap them out, and you get your new inverse or your inverse of that graph. Okay? That's pretty straightforward. Okay? Now, what you might notice is the green graph is actually a reflection of the blue graph or the black graph there. Okay? And it is a reflection, and this is something you would have or hopefully gone over in functions. Given a graph, okay, it's being reflected. You're reflecting the graph, and I'm going to show you this in a second, over the line y equals x. What is the line y equals x? Well, that's your most basic linear function. It is a line with a y-intercept of 0 and a slope of 1. It's this line right here. Okay. And what you might notice is maybe if you tilt your heads or kind of look at it here, that green graph is a reflection of that original graph. And we can look at it a little bit more closely by looking at kind of each specific point. So if we look at the vertex, notice how the vertex is one kind of diagonal away from that y equal to x line on both sides. If we look at our 0, 4, 4, 0 line or point, it's 2 diagonals away from that line on both sides. Okay. And if we look at our 4, negative 4, 4 and our 4, negative 4, again, that is 4 diagonals away on both sides of our line there. Okay, so those points are direct reflections over that line y equal to x. Okay, so that's kind of how you determine the inverse of a graph, or given a graph. Now, those two first ones are pretty straightforward, okay? Now, where we get maybe a little bit more tricky is with our given an equation, okay? Because this is really where we have to deal with algebra or get a little bit more intense with the algebra. Now, what you could do here is you could pause this. Well, let me just explain the first 3 steps. Then you can pause the video if you would like. Give this one an attempt. It is a little bit tricky, but we could give it a shot and then continue the video to see what the solution is. But when we are given an equation and we want to determine the inverse, we're going to go through 3 kind of first steps, kind of setup steps. Our first step is we're going to rewrite the equation. See if my pen can go smaller here, as y equals. Okay, so I'm going to take out f of x and I'm going to put it as y equals x minus 1 over 2x plus 3. Okay, so we rewrite it. We take out the f of x, we put in y. Step number 2 is we are going to swap. So just as we've been doing, we're going to swap x and y. Okay, when I do that, my equation becomes x equals y minus 1 over 2y plus 3. Okay, and our third step, and this is the one that will get you to maybe pause after, is we're going to now isolate. Well, not isolator, isolate for y. Okay, if you want, you can pause this video and you can attempt to isolate for y there. Okay, I'm going to go through the solution now. So I'm going to rewrite it over here and go through the steps with you. This is as far as I can zoom in. So I'm going to write, see how we do here. We're going to x equals y minus 1 over, 2y plus 3. Y minus 1, 2y plus 3. We're going to go x equals y minus 1 over 2y plus 3. All right, I'm going to do it over here. First thing I'm going to do here is I do not like denominators. I am going to cross multiply and get rid of this denominator. When I cross multiply, it becomes 2 bracket 2y plus 3 equals y minus 1. Now, we don't like brackets in when we're solving because they kind of trap those 2y and the 3 in there. They don't allow me to move those things around. So I'm going to distribute that x into that bracket. I get 2yx plus 3x equals y minus 1. Now, typically when we're isolating for a variable, what we're going to want to do is we're going to want to get that variable to one side. So in this case, I am isolating for the y, so I'm going to try to get all the y's on the same side. So that means I'm going to bring all my y's to the left side. Anything without a y is going to go over to the right side. We're going to go 2yx. That one y came over, so it becomes minus y equals. My 3x went over to the other side, where it's going to become minus 3x minus 1. Now the next step, again, this is a bit of a tricky question here, kind of showing you how to do it now. So hopefully going forward, we have some idea of how to do this. The next thing we're going to do here is we are going to notice that both of these terms have y's in them, and we are going to common factor out the y there. We are going to go, when I factor out a y, I get 2x minus 1 equals negative 3x minus 1. Okay, and you hopefully now notice that we almost have y all by itself. The last step that I need to do is I need to divide both sides by 2x minus 1, divide by 2x minus 1. And when I do that, those cancel out, and we are left with y equals negative 3x minus 1 all over 2x minus 1. And we can write that answer in inverse notation, which is f of negative 1 to the power of x, of x is equal to negative 3x minus 1 over 2x minus 1. And that is our inverse function. Okay. All right. Let's continue. Again, we'll give you, there's some practice for you to work on in the textbook there. If you have questions about that, you can come and see me tomorrow at lunch, and I can go over that with you. I've mentioned before, I'll mention again, this course is heavy on the algebra. Okay. Other notes. So one thing I do want to note that I didn't mention when I was graphing earlier, but one thing I'm going to mention here in terms of our graph. Okay, I'm just going to erase these lines so we can kind of just clear things up a little bit and then talk about something kind of specific here. Okay. What is our, think about this. What is our domain and range of each function here? What is our domain and range of the blue function, the blue parabola? And what is our domain and range of the green parabola? So I'm going to first do, our domain range over here. So our domain of the blue parabola is x is an element of all real numbers, or x exists for all real numbers. Okay, it's just a parabola. That's true for all parabolas. Our range for that parabola is that y is an element of all real numbers such that y has to be greater than or equal to 0. Okay, so that is our domain and range of our blue function there. Now, when we look at our domain and range of our green function, okay, again, you can think about this for a second. Kind of pause. If you want to pause the video at any time here, feel free to. Our domain of that green function is going to be x is an element of all real numbers such that, now notice how it is only goes to the right. The furthest point to the left on that green graph is at 0. So x is greater than or equal to 0. Okay. Our range for that green graph, notice the arrows at the end. That graph is going to go forever up and forever down. So its range is just going to be y as an element of all real numbers. And that is all. Now, what do you notice about our domain and range? Your domain and range swap. Okay. In the original function, compared to the inverse function, your domain becomes your range becomes your domain. And so again, we're just swapping x and y's. We're swapping our domain and range. Okay. And I'm going to just put that in the note here. Inverse domain. Well, let's just try and make sure I get my spelling right. Inverse domain and range are opposites. The original function. Okay, no other notes there. All right, that sums up that part. And now we are going to get into just a little application practice or problem, and then that will be all for today. Okay? Okay, so I'm going to read this question. I'm going to talk about application questions and kind of like just something important to think about with application questions when we're talking about inverse functions, because it's a little bit different, just slightly different. And I'll try to kind of make that make sense to you here. Okay, so this example says the owners of a candy company are creating a spherical container to hold their small chocolates. Think about at Easter time, you get those Easter eggs, they're hollow and they have little chocolates inside of them. Okay, but we're thinking kind of like that, but a perfect sphere. Okay, they are trying to decide what size to make the sphere and how much volume the sphere will hold based on the radius. The volume of the sphere is given by the relationship V equals 4 over 3 pi r cubed. It says determine the equation of its inverse. All right. So what we want to do here is we want to find the inverse of that equation. Now, typically, when we're looking for an inverse, our very first step is to swap our x and our y, or to swap our variables. Okay, in this case, our variables are v, which is volume, and r, which is radius. Now, because this question gives context, because there's context to this question, and like v actually represents something specific, very specific, like volume, and r represents something very specific like radius, we're not actually going to swap the variables in this case, okay? Because then if we swap them, it kind of takes away their meaning. And in this question, these two things do have meaning. They have, like I said, they have context. And so we're just going to leave these variables as is, and we are going to instead just isolate for r, or just rearrange and isolate for r, the variable that is not currently isolated for. Okay, and so what does that look like? Well, I'm going to go walk you through the steps here. Again, if you want to pause this video and try it on your own, you can do that. Otherwise, I'm just going to continue. Here we go. Whoa, apologies. So we have v equals 4 over 3 pi r cubed. The first thing I'm going to do is I'm going to multiply both sides by 3. That's going to get rid of my 3 in the denominator. So I have 3v equals 4 pi r cubed. I'm next going to divide by 4 pi. Those are going to cancel out. So I have 3v over 4 pi equals r cubed. Now, how do I get rid of a cubed? Well, I get rid of a cubed by taking what's called the cube root of both sides. Those cancel out. And I'm left with r equals the cube root of 3v over 4 pi. So that's my formula, or that's my inverse. Okay. Now, thinking about this, so the next question just says compare the domain and range. Okay. Well, for this question, all I'm gonna talk about here is, again, this is the more the reason I'm asking about domain and range here is because of the context of this question. Okay. So this question is talking about creating a spherical container to hold chocolates. So when we look at our domain in our original function, remember our original function was v equals 4 over 3 pi r cubed. Our domain is going to be related to our r value. Okay, so our r value. So r is going to be our independent variable, which relates to our domain. So now, do we have any restrictions on our radius? Think about this sphere. Are there any restrictions when this company is making this sphere on what the range can be? Can the range be any number, positive or negative? Well, no. The radius cannot be negative. You can't make a sphere that has a negative radius. So in this question, we're going to say that our radius has to be greater than 0. It's not even going to be equal to 0, because if our radius is 0, there is no sphere. Our range then, same idea. Our range is related to our volume. It's going to be the same idea. Your volume cannot be negative. Your volume can also not be 0, or else this company is not giving away any chocolates. There's no chocolates in those spheres, and there's a lot of disappointed children at Easter time. So we are going to say that that volume has to be greater than or equal to 0. And that is all we're looking at for our domain and range. Okay? Your domain and range of the inverse function would be the same. Last one here. Given this function f of x equals 5 bracket x minus 3 squared plus 7, it says determine the equation of the inverse. You can pause the video. I'm going to go over the question now. We're going to rewrite this as y equals 5 bracket x minus 3 squared plus 7. We're going to swap our x and our y. 5 bracket y minus 3 squared plus 7. And now we are going to isolate for y. I'm going to bring my 7 over. When I do that, I get x minus 7 equals 5 bracket y minus 3 squared. My next step is to divide both sides by that 5. I get x over minus 7 over 5 equals y minus 3 squared. I'm going to take the square root of both sides to get rid of that 2. I have root x minus 7 over 5 equals x minus 3. Is that, yep. And the last thing I'm going to do is I'm going to bring that 3 over, where it's become a plus 3. So I have root x minus 7 over 5 plus 3 equals x. Oh my gosh. Wait a minute. Look what happens when my writing's so messy. Those are y's. This is y minus 3. This is y minus 3. This is y. My apologies. Okay. And so I'm just going to write this in inverse notation, which is f to the power of negative 1 of x is equal to the square root of x minus 7 over 5 plus 3. Now notice that plus 3 is not underneath that square root sign. Okay, that is all for today. I'm going to put up your homework questions here. That was 37 minutes. That's about halfway through class. Our test is next Thursday, February 19th. There you go. And today's homework that I want you to work on right now is day 4, sketching graphs. These questions right here. Day 5, inverse functions. These questions right here. All right. Good luck. Work away at those. I'll answer any questions tomorrow during class, and we'll see y'all tomorrow. Have a great rest of your day.